one thing to notice is this gray one represents N2O5 and the blue one's NO2 and the red is O2. So this is just showing this is decreasing, these are increasing over time. One thing to look at though is if you measure the rate here, notice that you'll get a different value for if you measure the rate up here after 60 minutes or so of this decomposing. So therein lies there's some reason why, and it's because you're running out of reactant. There's not as much of it. So when you measure a rate using this, it doesn't tell us anything about the nature of N2O5. What's it doing? How is it falling apart? How exactly is it going into these two gases? So all we know from looking at this is that at the beginning it's faster than at the end. Okay. Another problem that complicates things is these two products can react and then start forming N2O5 again. So there's a method for determining this, and it shows this method shows is actually it's related to the number of collisions that the molecule makes. This can only be done experimentally, and it's called the method of initial rates. Okay, so here's back to this problem. Is if you measured it from 0 to 10, it's this, and 10 to 20, it's this. So you see that it slows down when it's a little bit when the reaction has been carried out for a certain amount of time. So and this also doesn't explain like why is it slowing down. So what's the nature of N2O5? How exactly is it breaking down? So there's a method called the initial rates, method of initial rates, and what you do is you measure you vary the concentration of N2O5, and you record how fast either the rate of disappearance of the reactants, and you vary it up with concentration. So what it does is it allows you to determine something called K and something called these exponents that each concentration gets raised to the power of. When x equals 1, it's called unimolecular. And again, these can only be determined experimentally. You can't tell from looking at the balance reaction. Unimolecular. When x equals 2, it's called bimolecular. And what this integer, the exponent, what it does is it tells you something about N2O5 and how these molecules are reacting, or how exactly it's breaking apart. So when it's unimolecular, it means it's dependent on the intermediate steps are dependent on one molecule. If it's 2, it's dependent on 2 molecules, and it could be trimolecular, where it's dependent on 3 molecules. More on this as we get towards the end of this unit. We'll see more of this. Okay. So for the reaction A plus B plus C, making products, the rate when you're using method initial rates would be equal to K, some proportionality constant called K. And as you see, this is dependent on, when you write rate laws like this, it's dependent on the concentrations of all the reactants. Okay, so let's take a look at an example. So yeah, I need to repeat this, that they have to be determined experimentally. So what I wanted to point out on this slide is that this is actually, for this reaction, it's considered a first order reaction, and you tell by looking at the exponent here that it's first order. And it actually, if you look at the balanced reaction, it has nothing to do with that 2. And if you look at this one, the coefficient is 2. but you have a different exponent. So the main point of this slide is just to illustrate that the rate laws have nothing to do with the coefficients in the balanced reaction. So, and it has to be determined experimentally. So let's take a look at some examples, experimental data. So the problem says determine the order and the value of K. So when it says determine the order, what we're looking for is we're going to write the reactant, and we're going to put an X here. So when it says determine the order, it's asking what is X. And when it says what's the value of K, obviously it's asking about that. So what you do is, for this reaction, and this one is like chapter 12, number 23. So to determine the order, you choose 2 trials and do ratios so that K will cancel out. So we're going to look at 2 trials, this one, and you could pick 3 and 2, it doesn't matter. And we're going to put rate of 2. So it's a clever method in order to get, in order to have a number here, because the K is going to be the same for all these trials. And so it allows K to basically drop out, and you could solve for just the exponent. So we're going to put rate 2 over rate 1 equals K this is for rate 2 and rate 1 X. So plugging in the numbers here, here's our rates. So we're going to put 2 over 1, rate 2 over 1, 7, 5, 10 to the negative 5th over 1.63 times 10 to the negative 5th equals I put the wrong thing here. So I need to plug in this number, 1.25 to the x power over k 0.74 to the x power. Okay, you'll see that when we do it like this, the k cancels, and then you have only one variable to solve for, which is x. So if you take 2.75 and divide it here, you should get, so this right here should be 1.7, and then this right here is 1.7 to the x. So therefore x must equal 1. Okay, so this reaction is first order, and it says now solve for k. So to solve for k, the next thing we're going to do is we're going to choose any trial and plug in exponents into the rate law. So rate equals k SO. So pick any trial from the experimental data, and now that we know what x is, we just put 1 here because we know that from the first part. And you could pick any trial And so I'll pick trial 3, 4.09 times 10 to the 5th equals K, and this was 1.86 to the first power. So when you solve for K, you should get 2.2 times 10 to the 5th. So what are the units for K? This is basically a dimensional analysis question. So K would equal molarity times second. So when you divide by this number, you'll have molarity. So for first order reactions, you'll see that the units are inverse seconds, basically. Okay, and then the last thing is to write the rate law. It didn't say to do this, it probably should have in the problem, but the last thing says to write the rate law. And show correct units for K. So we're going to write out K times 10 to the 5th inverse seconds, and you leave this blank and you put a 1 here. So what this allows us to do is calculate the rate for any initial concentration, since we know what K is and then we know what the exponent is also. So that's what it allows us to do, calculate the rate for any initial concentration. So that's the rate law. Okay, here's a kind of a shortcut method. So this is the time-saving easy way. Sometimes you can tell the order just by examining the data, so always check to see if that's possible before solving. So for example, looking at this reaction, this would be for the reaction we were looking at earlier. Looking at this data, if we did this over if we did this over this, that would equal 2. And then if we did this over this, so K would drop out, and then this divided by this would also be 2 to some exponent, and then X would equal 1. So sometimes the data, just check out the data before you go start plugging things into the equation, or trying to solve it with the method of initial rates. See if you can't do that just kind of in your head.